Greetings and welcome to the PLSQL channel, a series of video trainings on the Oracle PLSQL language. My name is Stephen Feuerstein and I'm a PL/SQL developer just like you. This lesson is part of my series on Say Goodbye to Hardcoding. It explores the different ways that hardcoding can appear in your code and then goes into detail about how to eradicate them. And this topic focuses on avoiding hardcodings in declarations. Some quick reminders. First, if you haven't already done so, go to PL/SQL Obsession, toadworld.com/sf, where you can download all the code I use in my presentations, as well as supporting PowerPoint documents. So here's PL/SQL Obsession. Click here to download my demo zip containing all the files that I use in my presentations. Training Seminars and Presentations offers you access to the PowerPoints behind my talks, and there's lots of other resources besides for you to check out. Next, make sure that you're comfortable with the material covered in the previous lessons in this series. Most importantly, introduction and concepts. What is hardcoding? What's the opposite of hardcoding? Why is it a problem? Hiding magic values and other aspects of hardcoding. But today, or in this lesson, what I want to do is talk about hardcoding that occurs in declarations. So, what's the problem? We'll take a look at fetching into records, using %type and %row type whenever possible. Use subtype to define application-specific types. So what's the problem? Well, first of all, a hard-coded declaration is a declaration that references the PL/SQL base types and or constrains the values in some ways. Let's take a look at an example. This is the same code that I used in my introduction and concepts to point out many different kinds of hardcoding. And what you see here at the top are a number of declarations that are both hard-coded to the base data type and constrained. So number is a base data type in PL/SQL. varchar2 is a base data type. And here are two examples of constrained data types. I specify the maximum size and the maximum precision for a salary value. I specify the maximum size for a full name. So those are examples of hard-coded and constrained declarations. Why might they be a problem? Well, usually, very often, our variables hold data that is stored somewhere else, most usually, in tables. We're querying data out of tables and into variables. If I hardcode my declaration type, then if the underlying column definition changes, I could get a value error exception, a -6502, or some other kinds of errors. So if I hardcode the declaration, it's disconnected from whatever the source of the data that it's coming from. And therefore, as that underlying source might change its structure, its size, its precision, my variable declaration doesn't keep up, doesn't automatically adapt, and I can end up with errors. So we want to keep things in sync, not let them go out of sync between our data and our variables in PL/SQL code. Let's take a look at a specific set of steps that you can take. First of all, fetch into a list of variables. If your fetch statement contains a list of individual variables, then you're hard-coding the number of elements in the select list. So this is an example of hard-coding, fetching into lists of variables. So I hard-code the number of elements in my select list, and then if the cursor changes, I have to change the fetch as well. And you can see an example right here. So I've got a select statement that selects 3 different elements. I declare 3 different variables, and I fetch into those 3 variables. And at first glance, that might seem, well, just fine. The problem is that I might add something else here, like the hire date. And now when I try to run my code, it won't even compile because I've got the wrong number of variables. I have to add another variable up here. I have to add the variable in my fetch. This is an example of hard coding. I change it in one place, and I have to make changes in several other places to accommodate the change. What do you do instead? Actually, it's really quite simple. Whenever you're fetching from a cursor, always fetch into a record that is declared using %row type against the cursor. Let's take a look. Now here's an example that really takes to an extreme the challenge of fetching into a list of variables. I've declared a package that has my cursor defined in it. This is a package level cursor, which means that multiple programs can all open and work with that cursor. I have my select list, and obviously the rest of my select definition defined right here. Inside my procedure process employee, I'm going to be opening my package-based cursor. So notice that inside this procedure, I can't even see what the select statement looks like. In fact, when you define your cursor inside a package, you can even create it with a return statement and hide the select statement inside the package body. So you wouldn't even be able to see the select statement in the package specification. Bottom line though, right inside this procedure, I have no idea. Do I have 2? Do I have 15 elements? Right now what I did was look up my cursor definition. I said, oh, I've got 3 values. Let's declare 3 variables. Let's fetch into those 3 variables. And it works today. But if along the way somebody comes along and changes this select statement, recompile the package, then this code will no longer compile. And it's quite a mystery because I can't even see the select statement here. I have to go look it up. So again, the solution is quite straightforward. Declare a record based on the cursor %row type. And then I can fetch into my record. This is one of those best practices that not only makes a lot of sense from the standpoint of giving you additional flexibility and avoiding the hard coding, but it actually saves you time. Rather than having to declare individual variables, you just make one declaration, %row type, against that cursor. And by the way, I think it's important to always %row type against the cursor. You might get lazy, for example, and do this. Here's my cursor, get me all the employee information for a given department ID, select star. In this case, what I could say is, well, forget about the package. Just make it employees, %row type. This matches my select statement today. But what I've done is made an assumption that my cursor structure will always match the table structure. And if I ever change this, if I decide, oh, I don't need all those columns, I just need 10 of them, then again, suddenly, my procedure will not work. So when you use %row type against exactly what you're fetching from, which is your cursor. Next up, do not expose constrained declarations and perhaps more generally any base data type declarations. Obviously, to declare a variable, you have to specify the data type. And if you're not careful, the way you specify that data type can result in a really nasty kind of hard coding. And generally, any declaration that relies on a constrained data type should be considered a hard coding. Now, what do I mean by a constrained data type? Going back to my hard coding example. This is a constrained data type. This is a constrained data type. This is an unconstrained data type. LDate is a date. LFlag is a Boolean. So this is unconstrained. And in fact, you can't constrain it. There's no way to limit how you declare a date. This is unconstrained. You can't constrain a Boolean. This is an unconstrained declaration, but it's also something to avoid because chances are you do want to specify some kind of limitation, or at least Oracle might change it over time. So generally speaking, what you want to do is avoid any kind of constrained declarations. And the way you do that, or the way to think about it, sorry, is to consider every varchar2 declaration in your application a bug, unless it's the single point of definition, the SPAD. This is the way I try to remind myself of the danger of constraints. You should never do a varchar2 100, a varchar2 20, a varchar2 10,000 declaration in your code unless it's the original definition of that type. In other words, virtually every varchar2 declaration that you'll find in your application, I believe, should be considered a bug. Again, the reason, let's talk through this. Right now what I've got is my full name variable is populated from last name comma first name. And what I did to declare it to be varchar2 100 is go to my database definition for employees and look at it and say, well, first name is 20, last name is 25, add 1 for the comma, that's 46. I'll double it. I'll make it 100. It's never going to get to be that big. So what I thought I've done is said, well, it's got to be a varchar2. I can't use %type, which I'll come back to in a moment, against a column because it's a derived value of multiple columns of information. So I've got to declare it as something right inside my code. So I'll just make sure it's big enough to never cause me a problem. But watch out for the word never when you talk about programming. It's never going to get that big? Well, today it can't get that big, but next year it might. If the DBA changes the size of first name and last name, then the combination of the two could easily exceed 100. So I've made an assumption here that the column sizes will never change, and therefore this assumption is always valid. That size will always be valid. That's a very dangerous thing to do, and it's the kind of thing you always do when you declare a varchar2 declaration, because you have to specify a maximum size. With numbers, you could always just say number. Whether or not you want to do that is another question. Salary 9, 2 reflects the actual definition of my column, and that's more important than just declaring things to be number. But the biggest problem is with varchar2s. So, what do you do about it? Well, spadification for data types, aiming for a single point of definition. So generally, two problems with hard coding the data type. The constraint could lead to errors in the future, like a 6502, because the column gets bigger. And second of all, the data type doesn't explain the application significance of the element declared. So when I declare something to be varchar2 100, all it's telling me is that the maximum size, the maximum size for that variable can be 100. That's all I know about this thing. I don't know, for example, that it's being populated with this full name expression or rule, last, comma, first. It's just a string. So that's not a whole lot of information. Same thing here. Number 9, 2. Why is it constrained to 9, 2? There's no explanation. It just leaves me wondering why it's that way and what happens if it gets to be too small. So we've got possible errors and loss of information, less readable code. So in general, whenever possible, and it's pretty much always possible, anchor your data types to a declaration of an already existing type. That means you are anchoring back to the single point of definition. And that way, if your existing type or SPAD ever changes, your code will be marked invalid and automatically recompile to pick up the latest version of the anchoring type. So I don't declare something to be varchar2, I declare it to be based on some other pre-existing type. And then all the definitions, all the dependencies are buried inside that other type. How do you do this? Well, the most common technique for spadification or anchoring of declarations, of data types for declarations, is %type and %row type. I can use %type when I declare variables based on columns and tables. That's the most common use of %type. But you can also use it to anchor back to other PL/SQL variables. I use %row type, as you already saw, for records based on tables, views, and cursors. Note that the lookup or resolution of the data type from these attributes occurs at compile time. There is no runtime overhead from using %type or %row type. Let's take a look. So in my original, I had these hard-coded data types, and I had my fetch into my list of variables. In my no more hard coding file, oh, and also, go back to one more thing, my department ID was hard coded as a number. No more hard coding now shows department ID is coming in as employees.departmentid %type. So it anchors back to the column in the table. If that's the kind of data that's coming in, I should comment it that way. I should document it that way. My local variables, if I chose not to use a record, here's my record %row type. But if I chose not to use a record, then I would avoid the hard coding of my employee ID and salary by tables.column %type. I'll come back to this last one when we talk about subtypes. So %types to define all my different elements that come from database tables, columns. %row type to reference back to cursors, tables, and views, and avoid the hard-coded constraints. Then, if my employees table changes, this program is marked invalid, and when it's recompiled, it will reuse or redefine my variable types based on the column definitions. Very, very nice feature of PLSQL, something you should use over and over again. And as I'd mentioned, but I don't document on this page right here, if you want to, you can also declare other variables based on the previously defined variables. So LID2 can be LID %type. So I can use the type of that other variable. It's less commonly applied in the world of PLSQL. Usually %type anchors back to a column in a table, but you can also anchor back to existing PL/SQL types or PL/SQL variables. Okay, So a lot of you know about percent type and percent row type, but a lot of developers are not aware of subtypes. Subtypes are one of the most trivial features of PL/SQL, but I think one of the most important. The bottom line is you can't always use percent type and percent row type in your declarations. You can't always find something in the database to anchor against. Sometimes you've got derived values. Sometimes you have application-specific types. And in these cases, what you can always do is define a subtype, which means a subset of an existing type or base data type, using the subtype statement. There are several benefits to subtype. Most importantly, you avoid exposing and repeating your constraints. So if I need to specify that there's a limit of, say, varchar to 100, I don't have to hard code it over and over again. I can define it once and reference it by name. I can give application-specific names to my data types. This is especially critical when you're working with complicated structures like collections of records and nested collections. I'll show you an example of that. But the bottom line is application-specific names to your types. And you can also apply constraints, such as numeric ranges, to the variable declared with your subtype. Here's the general description of a subtype statement. Subtype, the name of the type you're creating, is the data type you're using, and it could be a base data type or some other previously defined type in PLSQL. You can specify a constraint if the data type supports constraints. You can specify not null. If the base data type can be constrained, then you can also constrain the subtype. So for example, if you can specify a precision and scale on a number, then you can specify that as part of your subtype definition, even a range of values. And you can specify not null. Let's take a look at some examples. So here's a constant. As long as I named it C underscore, let's name it a constant. Now, here's my first subtype. Month number is PLS integer. So this is another name for the PLS integer. It's just an integer, but it's significant. It has to be a month number. What do we know about month numbers? That it has to be between 1 and 12. So I can specify a range of values. I specify a subtype called myNumber1, and it's number 4, 2. I've constrained the size of my number, specific for this one. A common example of this would be more like currency. Let's add another one here. So I might have a currency T, and in this case what I've specified is maximum size is 10, maximum precision 2. You can only have $2 and cents essentially, up to 99 cents to the right of the decimal point. I can constrain another type, one subtype from another type. So I've carried on my previous subtype into a new type, and I can specify my constraint there. Here's an example of specifying a not null requirement. So integers can be null, but this required integer is not null. All right, then I'm going to run my code. I'm going to specify 13 as a month number. Well, that's not a valid month number. Let's see what happens. I'm going to specify a value of 10,000 from my number 42, which is based on my number 1, which has a limit of 4 digits to the left of the decimal point. Same thing here. And let's try it out. So I ran through, no errors because I did my exception handling. Let's see what I get. Notice numeric or value error. This happened on my first one. When I tried to assign 13 to my month number, Oracle said, no, that's not a valid month number. When I tried to set 10,000 to my number 4, 2, it said number precision too large. So what this is showing you is that you can use subtypes to not only hide the details, give it a name that tells you exactly what type of integer it is, but also apply rules that Oracle will declaratively, you can define them declaratively, and Oracle will apply the rules for you. You don't have to write the code to do that. So these are some of the features of subtypes. Obviously, the feature itself is quite trivial. You just declare a new name type based on some other type, and then you can have some fancy fun with ranges and constraints and not nulls and so on. But the main thing is hiding the explicit definition behind a name. And I find these most important and most useful when I'm working with my application-specific types. So first of all, generally, whenever you're about to write a var-char2 declaration, a constrained declaration, stop and ask yourself, what kind of assumption am I making here? Is it really possible to say it's never going to be bigger than 300? Or am I always going to declare my variables to be like 32, 7, 6,